Hey, hi, Fenru.
Hi.
Okay, so you are taking care of this session?
Yes, I think I supposed to do that, right?
Hey, hi,
Because
Siddharth.
Hello.
hi.
Okay, are you guys both handling this one? Siddharth, I don't see your name here.
I think I will take care of this part
Yeah,
because today is Thursday in America and 10 from 10 to like 10 a.m. to p.m. and we'll responsible. I'm
correct.
responsible for the W5. Oh yeah, there are two W5.
The second one is cancelled.
Oh, second one is canceled. Okay, I got you.
I
Yeah,
think.
actually, I got the message from Professor Young to coordinate in this session. That's why I
Oh,
also
I
joined.
see. Okay, good.
Oh,
Yeah, that's good.
mhm.
So we are still waiting for the organizers, right?
Yes.
Yeah, from what I was told, the second day of RSP is cancelled. So that's probably good news for you guys.
Okay.
Yeah.
And it will start in like 10 minutes.
Yes, yes.
Okay. Mm-hmm.
So
Well,
did you guys, were you able to have a dry run with the organizers?
what what the you mean the BIOS?
No, did you have a dry run, like a meeting, a pre-meeting?
Oh, dry run for the for this one. Let me check my record.
I mean, Siddharth, did you have?
No, I didn't.
Okay,
Yeah.
okay.
Hi everyone. Hi Abra.
Hey, hi, Hosok.
Okay. Is everything okay here? I don't see any RSP people.
Yeah, maybe they're still coming.
Okay. Okay. Yeah, and Nox and memo code are okay.
Yeah, I checked both of them.
Okay, great.
Yeah. So I'll go and check the code AI.
Mm-hmm.
But I just wanted to know from Fengruo if they did dry run with the
Oh,
organizers or not.
yeah, I sent them the like invitations, but the organizer just replied to me to say that if there are any dry runs, I replied, but then there's no response.
Okay, so there was no dry run.
Yeah, no dry run.
So it was Frederick or Sungju?
You
Do you
mean the
remember?
pre-recorded videos?
No,
No, for
Who
the
you?
dry run.
Yeah, for the dry run.
Oh, it's like yeah, Frederick.
Okay.
He
Frederick.
found me, but didn't show up in the dry run.
Okay. Did you already send them Zoom link?
Yes, I
Oh,
sent them the Gather Town link or also the Zoom link, but no one comes to me.
okay, then I'm gonna go back together, and if I see Frederick, then I will let him know how to join.
Okay.
Okay, so you guys, maybe there is some time.
Mhm.
Okay, I'll check again. Let me check the other workshop.
Yeah, okay. Hi Fenro, I see one of the organizer like in the Gather Town.
Let me check.
Amar Amer Amar Baghdadi, like in front of the room 3.
Frederick.
No, the third or fourth one, fourth
Fourth.
organizer.
Monermi.
Amer.
AMER. Armor.
Yeah.
Let me check the mail list. 5 RSP. But Armor is not our organizer session. The organizer for our session. Huh? Oh, this one. Oh, he might be the speaker. But I also see the organizers. Let me check.
Okay.
Mhm. Oh, okay. He's in another room. Okay. Okay, we can just probably wait because
Yeah, that would be like good.
yeah.
Hi Siddharth, hi Pano. I have just noticed that they have different schedules, so they didn't reflect these changes in the ESWeek webpage, but I found out that in their webpage it starts not now, but in 45 minutes.
Okay, so we should wait another 45 minutes or until like 11 a.m. in US time.
Oh, let me quickly check. They put up all the information in European time, so it's a bit.
Okay,
But if you click on the URL that I put in the link, then it actually starts at 5 o'clock in European time, which is in 15 minutes. So
okay.
maybe we
It
need.
starts at like 5 o'clock, or
Yeah, you are in Europe right now, right, Siddharth?
it's 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 like 4 p.m. Uh, in Europe right now.
Uh,
4
I
6.
We
So
didn't make these changes in the ESWeek webpage, but it turned out that they made these changes in their webpage, so people know the time. That's the reason why nobody shows up yet. So
So
yeah, I'm gonna make an announcement on Gather, and then okay. And I sent out the emails to organizers, so they will know.
okay.
okay, I check the like conversion table. It maybe we have more 45 minutes to
Yes.
wait. Yeah, okay.
Thank you.
Mhm.
Okay.
Okay. Pengru and Siddharth, did you guys know that the workshop is going to start at?
Yeah, after like 40 minutes.
Yeah,
Professor Young informed like just before you came.
yeah. So, okay. Yeah, I mean, you can drop off and join like 10 minutes before that, 15 minutes before that, or you can hang on however you guys want it.
Okay, sure.
Okay. Yeah.
Thank you. Mhm.
Thank you.
Yeah. I checked the ESWeek website as well, and Fisu made changes, about the starting time. So yes, we just didn't reflect these changes in our internal Google Sheet, so I think it's okay. So the session will start in 15 minutes. And I saw Sungju is already here.
Were you able to talk to him?
No, he was not responding.
Okay.
But I sent him an email and
Pengru, maybe you can create a slide, right, with in the ESWeek format, right, with saying that RSP is going to start at use European time.
Oh, so I should like send an announcement to say
No,
that.
just create a slide and share that screen so that anybody who comes here will know that, okay, it's going to start at.
Oh, okay. So
this
I will send them the email. Okay.
No.
so
I'm
you
saying,
have a cover slide?
Or I can create. Yeah.
yeah,
if
okay,
I-
Siddharth.
Yeah.
Yeah, we use the European time. Okay,
Yeah,
see,
sure. And
yeah.
it will be 5 o'clock, right? European
Yes.
time,
Yes,
5 p.m.
Yeah.
No, that's not true.
Actually opening started at 4:50.
Yeah, 1650.
50.
1650.
Okay, sure. I'll mention that.
Yeah.
Abira, do you want me to make an announcement in Gather Town information board about the starting time?
Actually, that's not a bad idea, but I'm waiting for the slide to come up before I
Okay,
leave.
sure.
Yeah, I think you can go and make that.
Okay, great.
Yeah, this is pretty good. You can make it like workshop or just put the workshop
Full
name.
form. Okay, full
Yeah.
form. Okay, I can.
Yeah. I would say just write 33rd International Workshop on Rapid System Prototyping in the top as the title.
What was the number of workshop?
Yeah, just remove session. Start 33rd International Workshop on Rapid System Prototyping. Actually, 33rd is maybe, yeah, 33rd International Workshop. International Workshop on, yeah, okay, perfect. Okay, good. So now I can leave.
Hello.
Hello.
Hi.
Hi.
So my friend Sanju told me that there was probably some issue in the time zone.
No, yeah, actually, so Frederick made some last changes in the schedule, and we reflected this change in our web page, but we didn't reflect the change on the easel just in front of this room. So maybe some people probably arrive early, then in order not to miss these people, we will show this slide like this day.
Thank you. Thank you. Thank you.
Thank you, Amin. Thank you for this.
Yeah, thank you. Yeah, Sanju sent me a message, so yeah.
Mhm. Yeah, but I checked that information is correct on our webpage, so hopefully,
Yeah.
people will not get confused. So
Thank you very much.
thank you very much. So in case you have any difficulty, then I will be here around. So
Great. Thank you. And so, in fact, when the speakers will will share their screens, etc., how it works,
okay.
they have access automatically to share their screen. Okay, all people seems to have access to share.
Oh, I think so. So
Yeah.
and just to be on the safe side, if you already have their slide, then maybe you can send it to our volunteer student.
No, I don't.
Don't have it. Okay. So actually, we have collected all the slide and backup video. I mean, just as a backup for these technical sessions for ESWeek. So some of them have the difficulty on sharing their screen. So in that case, our student could back up. So,
It
but
was. It's really it's a good idea, but it's too late now to apply.
yeah, probably, yeah. But
No.
yeah. If you
Okay.
can send them an email, then we can still, if they want, then they can send their slide to our students. So I can give you the
Yes.
email address of our.
Yeah. Okay. So I can send an email telling them that if they wish in advance, this would be a good idea.
So this session is in charge of Fanro.
Yes.
Okay, his email address is. Okay, I will just put it in the chat.
Yes, please. Okay.
And Siddharth is also here.
Okay. No, that's okay.
So Fanro is in Delaware and Siddharth is in Germany. So
Okay.
Okay.
Okay. Thank you.
Okay, thank you. So I will be here around. So if you have anything, and just let us know.
Thanks.
Thank you.
So see you later.
See you later.
Bye.
Bye.
Hello, Fred. Do you hear me? I don't hear you. It seems like you are trying to talk.
We can hear you.
Okay, thank you.
Do you hear me? Amer?
Yes,
Is-
yes,
is it
Frederick.
fine?
Now. Yes, yes, yes.
Amer,
Yes,
do you hear me?
yes, yes, yes.
I cannot hear you.
Yes, I hear you. You have a problem of voice, so. Yes.
For the ESWeek staff, I have some slides, so I don't know if I can share it instead of yours. Okay, thank you.
Now, okay, you hear us, Frederick?
I'm a bit embarrassed because I have no sound.
Allô?
Hello, Mustafa.
Ça va bien?
Yes.
Okay, so I think it's good now.
Hello.
You hear us,
Hello.
Fred?
Yes,
Yeah.
yeah, it's perfect.
Good, good, good.
I forgot to plug in my earphone, so that's better with that.
Yes.
So I suggest to start. So if you agree on that. So I would like to welcome all the participants of this 33rd International Workshop on Rapid System Prototyping. So I was one of the two general chairs this year with my colleague Kenneth Kent. I would like first to thank very much all the program chairs. So we have 3 people, Amer Baghdadi, who is here from the EMT Atlantic in France, Sonju Yeo from the Seoul National University in Korea, and Junian Tan from Changzhou Institute of Technology in China. So really a very good thing to have organized that event with all the process of the selected papers. So this year it's still a full virtual event, so I hope it's going to change next year, and we will have the chance to be face to face for the next edition. This year we have 3 sessions in this afternoon. So 3 sessions. The first one is about application-specific designs for vision. The session 2 is about processors and systems, and the last one, the session 3, it's about analysis and trade-offs in architecture and prototyping. So we have each time 3 papers in each session, which will be followed by a 15-minute break. And then for each paper, so we expect about 10-12-minute talks and 3 minutes for question and answer. So it's a Zoom platform. So all the speakers have to share probably their slide. And I'm going to ask also to all the speakers just in few words to present himself. Amer as program chair, one of the program chair, do you have something to add? Maybe just to present yourself to the people. I forgot to say that my name is Frédéric Rousseau from Team in France, and I'm one of the organizers of RSP for, I don't know, 20 years or something like that. Amer?
Yes, so I'm Baghdadi from IMT Atlantic. So yeah, welcome everyone in this in this 33rd edition of RSP. I have sent an email. I have nothing special to add unless that if there is. I have sent an email to speakers in case there is any issue in slide sharing. You can send your slides to the addresses that I have sent by email half an hour ago. And sorry for the timing. So for people in Asia, it's now midnight. So really sorry for that. But I mean, yeah, there is no good time to arrange the whole world.
Okay, thank you, Amer. Maybe one word from Sanju and then Junian. Sanju, I have seen that you join us.
Yes, I'm here.
Okay, so
Thanks
Sanju.
for the yeah. My name is Junyan Tan, and I come from Changzhou Institute of Technology in China. Thanks very much for today for the program chairs. Thank you very much. Yeah.
So okay, so it's more than midnight. So I hope you will stay a bit with us.
Yeah.
Before the night. Okay, thank you, Junian. So Sanju.
You're welcome. Yeah, Changzhou.
Hi. Yeah.
Okay.
Hi, I'm Songju Yu at Seoul National University. Yeah, welcome to RSP. Yeah.
Okay. So we will go to the. Oops, sorry. Okay. So I think we should start with the first session. The first session is about application-specific design for vision. So I'm going to chair this session. I don't know who is the first speaker. Probably Mustafa Riz. I have seen in the attendees. So I will stop sharing my screen, and Mohamed, you may start.
Okay, thank you. I will share my screen first and be sure that you can see it.
Yes, that's perfect. Okay, so you should start for 10-12 minutes.
Okay, thank you all, and hello everyone. I am Mustafa Rizk from Labstic, France, and I will present our recent work about marine object detection using deep learning on embedded edge devices. As you know, convolutional neural networks have been introduced to handle the challenge of object detection. However, real-life applications impose the requirements of accuracy and precision, as well as ensuring real-time detection. These requirements come with a high cost in terms of computational resources. Accordingly, the implementation of CNNs
introduces a challenge, especially when targeting edge devices with limited energy, budget, and computational resources. In this work, we make use of efficient optimization techniques enable to do runtime detection of marine objects using CNNs while applied on edge devices. Recently, You Only Look Once YOLO method has been introduced as an efficient unified model of all phases of a CNN for detecting multiple objects in real time. Several versions of YOLO exist with different architecture specifications suitable for embedded systems and low power modes. In this work, we aim to investigate these models in detecting marine objects and examine their performance. In particular, this paper presents the work done targeting YOLO v4 and YOLO v4 tiny models. In this work, we followed the well-known method for AI detection, starting from the creation of a dataset and the steps of training and validation of the models, then evaluation, optimization, and finally deploying the optimized models on hardware devices. Concerning the dataset, we have created a diverse dataset of marine objects, which has the widest number of classes and annotations compared to available datasets. It comprises approximately about 28,000 images with 35,000 annotations that refer to 41 classes of marine objects. The collected images are all processed so that images without annotations are labeled manually, and available labels are converted to YOLO format and enhanced by adjusting the bounding boxes to meet the exact dimensions of the target marine object. Also, images which are too similar in the same class are removed, and similar classes are merged in order to avoid confusion while detection. Note that the collected dataset includes images that are captured using imaging cameras with either RGB visible or infrared sensors. The included images are various and differs in terms of resolution, scale, and have different number of objects in each image. For the training, it is done using the DirectNet framework on NVIDIA RTX 3090. We have used transfer learning in order to maintain generalization by starting from models previously trained on the well-known huge COCO dataset. We use also different data augmentation types such as cut mix, mosaic, random rotation and exposure and hue. We have downscaled the images to resolution of 416 and in other cases for 608. The batch size is limited to 32 images using an RGB channels. So we use 3 channels for training, and the training process is conducted for 79 epochs. During the training process, the trained model is validated using the validation dataset, which is a small part of the original dataset. Starting from 1,000 iteration, the mean average precision is calculated for each 4 epochs. This figure shows a sample training and validation performance of YOLO v4 model. The blue curve in the is the training loss, whereas the red curve is the mean average precision calculated while training after each epoch. You can see in this figure that we have reached about 83% of map. In addition, all the trained models are evaluated using several popular metrics in the field of object detection. This table presents the obtained evaluation results for all trained models with different architecture specifications and while adopting different augmentation types and input image resolution. As a summary, it can be noticed that high map values are achieved in most cases and that data augmentation improves the precision. Also, the use of higher image resolution lead to slight improvements. The obtained results demonstrate the effectiveness of trained YOLO v4 and YOLO v4 tiny models in detecting marine objects. This shown image presents a sample detection. As you can see that the detection are done or attained with a high confidence ratio. In order to achieve high speed inference with high precision detection, we apply optimization techniques. So the first thing we have done that the YOLO v4 model is pruned at the level of channels and the levels of layers. After that, fine tuning is applied to assess the pruned model in order to restore the accuracy. This table presents the obtained results after each pruning step. You can see that fine-tuning of the YOLO v4 network recovers the accuracy loss due to sparsity. The obtained results show that the fine-tuned network still achieve high precision, as you can see here, while reducing the memory need by 97% and the computational resources by about 88%. Later, we deploy the models on emergent embedded edge devices such as Crea AI Vision from Xilinx and Movidius VPU and NVIDIA Jetson Xavier AGX. The common steps for deployments are a quantization step to reduce the bit width of weights and activations using heuristic method and a golden reference pool of images selected from the trained dataset, and followed by a compilation step to optimize the model based on target hardware and then mapping it into optimized instruction sequence ready to be deployed on the specified hardware. For the Jetson Xavier, we used Tensor RT RDX from NVIDIA. Tensor RT does like a back-end hardware optimization, which implements several techniques such as kernel fusion, precision calibration, kernel auto-tuning, dynamic tensor memory, and multi-stream execution. The presented table shows the obtained results. We can see that using Tensor RT increases the inference rate while maintaining accuracy of all tested networks. For example, for the tiny YOLO network, the inference rate is increased, but at the cost of the degradation of the performance by only 2.2 and 2.4 points in map for the FP16 and FP and INT8 quantization. Whereas for the YOLO v4 model, the FP16 quantization leads to an increase of the frame per second by about 3 times and about 8.5 times, with a slight degradation in the map of 2.9 and 4.1 points. I will present also the result attained when deployment of the method of the models on Crea AI Vision Kit. So using Vitis AI, the trained model is quantized into INT8 representation, which is the only supported one by this board due to the specifications of its DPU. This table presents the obtained results in terms of detection, performance, and inference speed of the deployed models on CreaKit. It shows that YOLO Tiny can achieve up to 60 frames per second while maintaining a map value of about 74%. The pruned YOLO v4 model can achieve an inference speed of 50 frames per second, but with a significant degradation in map. So we have a loss about 24 points. While the unpruned YOLO network can achieve the best map, but with a limited inference speed of 11 frames per second. At last, thank you for your attention, and I am ready to answer your questions while watching a short demo video.
Thank you very much.
It's on time somehow.
Okay. Is there any question in the audience? Yeah, Siddharth.
Yeah, thank you for the nice presentation. I have one question, like how do you decide what kind of what is the criteria when you use the pruning in your models? This is the first question which I have.
Okay, for the pruning, we first do a test on some epochs. For example, as I said, the pruning consists, we use like a method that take a big amount of images from the data set and put it like in a pool. And then we start doing like structural pruning with different criterias. And for each iteration, the developed method test the performance. If it's okay, it continues for other layers and so on. If not, it starts with another type of pruning. And we do this for about 300 epochs, which is a big amount of epochs or iterations. And when we reach to an acceptable performance in map, we assume that pruning will achieve a good results, and so we continue with the pruning.
Thank you, Siddharth.
Okay,
Do you have another question?
Yeah, I
No?
have
Yeah?
another one also. Can you please go
please.
to slide number 11?
Yes, for sure. Yes.
Yeah, as you can see, like in the yeah, first, like why did you use like leaky relu and MISH activation function? I'm not familiar with MISH activation function, but like what is the reason behind that? Why didn't you use normal relu or like any other sigmoid or anything?
First, the mesh is the, if you go to the YOLO paper, YOLO V4 paper, they introduced like mesh is the best solution for attaining the best performance. And there is a lot of simulations where they compare between different activation functions. But the issue that we have target also leaky relu for one reason, that rather than mesh, that one of the devices that we have used, which is the Kriya board, does not support the mesh activation function. So we were somehow obliged to transfer or change the structure of the network by changing all the mesh activation functions and convert them into leaky relu. Because in this type of kits, we have like a dedicated DPU with pre-defined functions that we cannot change. So for that, we did like this combination between leaky relu and mesh so that we can deploy our trained models on different architectures or different available edge devices.
Okay, yeah, one quick like comment on that. As you like see, while using int 8, like 8-bit quantization in different different columns of your row on the same slide 11, you see
sorry.
like there's a degradation of uh, accuracy or whatever, like it is precision or recall, whatever. I would suggest like you can try dynamic quantization also. With the 8-bit, you can achieve much higher accuracy compared to like baseline and floating point. Yeah.
Thank you for this information. But here we are somehow limited to the procedure in TensorRT. So in TensorRT, you cannot define your own precision. Because here the optimization is done directly on the hardware itself. It's not done on a host computer, for example, GPU that you can define your network and all their methods. So in TensorRT, you are obliged for each device, you have like a package, a certain supported package by TensorRT for optimization. And according to this, they specify what are the supported floating point or supported quantization. We cannot choose by ourselves how to do this, for example, gradually or whatever, and so on. So it's somehow different from doing this, for example, using PyTorch or TensorFlow, doing it on a GPU, because here we do the optimization according to the specifications of the embedded hardware.
Yeah, I see. Thank you.
Okay, thank you. Any
Thank you a
other
lot.
question? I may have one. I was wondering, is there a specific constraint in this marine object detection compared to some other object detection you can find, I don't know, for a car or something like that? What is very specific, in fact? Is there something very specific?
There is a lot of challenges, but one of them, which is somehow related to the dataset itself, because it's a very critical point, is that most of the marine objects are similar to each other. So, for example, a boat, if you are looking for a boat,
okay.
it's similar, for example, to a big vessel if it's far from you.
Okay.
And also there is a lot of challenges dedicated to the input data from the image. For example, you have the change of lighting on the water differs, for example, between according to weather, according to the timing in the day, between day and night, and so on. So this construct a lot of challenges, especially that you have the motion of the chip or the object and the tides of water that can be similar in most of the image beside the ship or apart from the ship. So we have a lot of challenges, especially, for example, if you take the horizon, the effect of the horizon is very sensitive or critical in these cases, and affects a lot of how the model is trained and how it can build its filters.
Okay, I don't know how we can upload the speaker, but thank you very much for this talk. So I think we will go to the next one. The next speaker is probably Sanjup Khan from the Seoul National University. So maybe Mohamed, if you can.
Okay, well, I will.
Mustafa, if you can just stop sharing your screen. You need to stop sharing. Okay, yes. Perfect. So Sanjup Khan, okay. It's perfect. So, okay, we can see your slide.
Hello, can you hear me?
Yeah, perfect.
Right?
Yeah.
Okay, hello, thank you so much for joining me in this workshop. My name is Sanjup Kang from Seoul National University in Korea, and I'll present our paper, ternary nerve, quantizing voxel grid-based nerve models. So I think many of you have heard of nerve, since in the past 1 or 2 years, there have been many papers pouring out on this topic. The reason why this technique is gaining so much attention is because it is the very technique that can be used in most of the VR or AR applications in the future. So at first, I will introduce you to a little bit of background on neural readiness fields. As you can tell from the name, it is to have a neural network to learn the readiness fields. Simply saying, the neural network learns the shape and appearance of 3D objects or scenes given a set of 2D ground truth images. So once it does so, you can render the image from any distance or any direction from the object, which is exactly what we want to do to achieve our realistic experience in the virtual space. So again, the goal of training nerve is to render 2D images of 3D objects from any viewpoint. To narrow down the problem, you can think about like how we render a single pixel of an image. So we cast a ray from the camera like this through the pixel and sample a few points along the ray. Then we somehow compute the density and color on each sample point and accumulate them to obtain the color of the pixel. So here, what we want the neural network to learn is the mapping between the sample points with its corresponding density and color. The authors of NERF showed that a large NLP here is pretty good at this, even when the object is very complicated. By the way, before they give the coordinates as input to the NLP, they take free features of the coordinates, you know, the cosine and sine things, to better learn the reference fields. However, this could not be used in practice because the size of NLP was too large. It required 8 layers of 256 channels. So carrying on every sample point took long, that it took about like 30 seconds to render a single image. So to overcome this severe disadvantage of this method, many improved version of NERF has followed, as you'll see now. The idea is if you have a properly learned feature vectors rather than the Fourier features, you can highly decrease the size of NLP. One approach is to realize this is to have a 3D voxel grid where we store a feature vector at every vertex of the voxels. To carry on a certain point here in the 3D space, we find its surrounding voxel to extract feature vectors, and we process it with NLP to obtain the density and color at the particular points. Many papers report that this voxel grid-based learning enables much faster training inference by having much smaller NLP compared to the previous method. However, the problem of this approach is, as you can guess, the 3D voxel grid is too large in size. Therefore, in our paper, we studied to compress this voxel grid by applying the lowest quantization on the feature vectors. At this point in time, there are 2 state-of-the-art papers, which are InstantNerf and Tensor. We'll test the efficacy of our method by applying quantization on these 2 powerful baselines. So before diving into our main methods, I will give you a 1-minute introduction about those 2 baselines. First, InstantNerf stores the feature vectors in hash tables like this, rather than in a 3D structure. So each vertex is mapped to one of the entries directed by a randomized hash function. This way, they reduce the number of parameters by having multiple different vertices to have the same feature vectors. And as they have multiple grids of different resolutions, they also have multiple hash tables for each grid. And from those tables, they fetch and concatenate the feature vectors, and they feed it to the subsequent NLP. In Tensor, they compress the size of 3D voxel grid by factorizing into a set of vectors and matrices. So you can think of it as the extension of matrix decomposition, like SVD or PCA. The same way here, they have many components to represent the high rankedness of the 3D objects. And they fetch features from each component, and their concatenation here is processed by the following NLP. So rather than directly jumping onto quantization, we did a toy experiment to see like how what feature vectors learn to represent an object or scene, to get some hints on designing our quantization scheme. We train the model on a simple 2D image on the left and obtain the feature vectors you can see on the right. So from the learned features, you can observe 3 different patterns to represent each shape. For example, you can see a blue color inside the circle, a red line on the boundary, and a white background outside the circle. So this pattern is consistently observed on the 2 other shapes like triangles and squares here, which made us imply that you may have to store only 3 different states of the features to represent any geometry or color, even when the object is kind of complicated. So we are motivated by this observation to see how ternary quantization will affect the performance of the model. To achieve efficient quantization appropriate to the NERF models, we adopt the 4 following strategies. So let's see from the first one in a detailed manner. First, we argue that not all the parameters should be quantized. Since MLP, for example, is known to be very sensitive to perturbation and expected to harm the rendering quality drastically after quantization, we exclude them from our quantization targets. And furthermore, we also maintain some of the parameters in high precisions if they account for a relatively small portion of the entire model. For example, for instant NERF, we only quantize the hash tables, let alone the non-hash small size tables. Also for TensorF, we only quantize 2D matrices because the 1D vectors are so small that they contribute very little to the entire model size. Later on, I will show the effect of this strategy as the ablation study. And as the second strategy, we carefully choose the granularity of the parameters. Basically, finding the optimal quantization parameters, say scale or bias, is known to be very important to prevent the loss of information from quantization error. This is especially effective when each group of parameters has its distinct distribution. So that's why determining the quantization granularity in an appropriate way is important. For example, if the 2-dimensional parameters is your quantization target like this, there will be 2 options. One way is to divide it into multiple rows along the dimension, the dim1, like this. And another way is to divide it into multiple columns. Of course, it will give different results depending on which dimension you choose. So we did research on the 2 baseline models to see which dimension you have to group the parameters along. For instant NERF, choosing the granularity is pretty simple. The plots here are the distributions of featured elements of 16 hash tables. Since each table manifests its distinct distribution, we set each hash table as a single granularity. For TensorF, though, it is a little more complicated. As mentioned, our quantization target is a set of 2D matrices. So you can think of the figure on the left as the picture of stacking up the matrices as many as the number of components. If you plot the distribution of each component, you have different distribution, as you can see on the right. This means grouping the parameters component-wise could be effective. However, when we do the same thing element-wise, we also discover that each element has its own distribution. This means we have to experimentally choose one between the 2 choices. So later on, we will show which granularity provides larger improvements. To reach more stable results, we apply 2-step quantization. For the first half of the training phase, we pre-train both baselines in the high precision setup, and then we switch it into 2 bits or ternary setup as a fine-tuning phase. The pre-training phase provides a good initialization of the model, allowing for more stable results at the end of the training. Lastly, we try to maintain as much information as we can learned by training on high precision. As I explained in the introduction part, you have to query on many sample points independently, which takes a long time. But if you know which part is occupied by the object as a prior, we can skip unnecessary points where objects does not exist. To the end, both baseline models have an occupancy grid, which is supposed to be updated in the training time. However, we find that it should not be updated in the fine-tuning phase because the quantization error will rather harm the faithful information learned during the pre-training phase. So you can also see from the figures on the slide that the learned features of ternary nerve are more similar to the high-precision ones when the occupancy grids are not updated in the fine-tuning phase. From now on, you'll see the results of our implementation. I talked about the two options of the quantization granularity for TensorF, and this is the results that I got from training the model for each setting. There's a trade-off, like the element-wise gives you higher PSNR, but sacrifices a little amount in the model size compared to the component-wise setup. We choose component-wise, which provides smaller model size, but as the difference is slight, we leave it for the user's choice. And we tested our quantized version of the two baselines on the nerve synthetic data sets, and this is the PSNR we got. Despite the aggressive quantization, we observed only slight degradation in PSNR metric, not even larger than 1 decibel. As an ablation study, you see that we obtain much better results when we exclude some of the parameters which are sensitive to quantization. And the resulting rendering shows that the ternary nerve well preserves the representation of the object. Our work offers a large amount of reduction in model size from like 7 times to 15 times at a negligible loss of image quality. You can also see little notable difference in other data sets also. So as future work, we actually have succeeded to reduce the model size, but we kind of failed to actually speed up the inference or rendering. So our future work will be to look through the reason why it didn't lead to faster rendering. And also, we only tackle with the static objects under single illumination. But in real world, the objects may move or experience different light conditions. So another future work is to explore what more techniques will be required to apply our quantization scheme to wider applications, like dynamic or relate objects. So that's it for my presentation, and please refer to our paper for more details. Thank you so much.
Thank you very much. Is there a question in the audience? Okay, so I have just, okay, we speaking?
Yes, I have a question.
Okay.
Thank you for, the results are impressive. Regarding comparison of quantization, did you have compared with what's the gain that we could obtain with respect to other quantization methods with respect to ternary that you have used?
So you're asking about the results between the baseline and the ternary quantization?
Yes, here, yeah. Can you comment? Yes, so you what's so here the comparison you have done between the baseline and ternary.
Yes.
Can you comment again this slide, please? That was a bit quick.
All right, so you can see from the last column the compression ratio that for instant nerve, you obtained 7 times, about 7 times reduction in model size when you apply ternary quantization, and for TensorF, you achieve 15 times of the reduction in model size, while maintaining the PSNR to a comparable degree. So you can see the like 0.3 or 0.5 decrease in the PSNR, average PSNR. And this is very slight loss in PSNR metric. So yes, we did, yeah.
Okay, thank you.
Okay, thank you. Mustafa, it seems to me you have a question.
Yes, just for curiosity, did you apply or compare other types of well-known quantizations? For example, the End8 quantization, what's the effect in terms of inference and at the same time in terms of the performance on the model size?
Sorry, I'm afraid I couldn't understand. So
For curiosity only, why did you choose ternary, not other type of quantization?
all right. So yes, we could have tried other bits like 3, 4, 5 bits, but we are motivated by the observations that you can see here in the slides. That again, when you train any image, any objects on the model, you have those ternary patterns on the feature vectors. So you have 3 different patterns which are on the boundary. You have the red lines on it, and inside you have blue colors, and background is white. So we observe the same patterns for almost every objects. So we were we wanted to see, like, if we only maintain ternary states of the feature vectors, could we obtain the same or similar rendering quality? So that was our question. So we wanted to test it. And of course, for other bits, other bit precisions, we also expect we'll have similar effects on the rendering quality.
I have another question, if you please.
Yes, please.
If time.
Yeah, of course. Yeah.
So I understood that you have done the training without any quantization, and then just you have done like a fine tuning with the quantization. That's what you have done.
So
that's correct.
Yeah, yes, it's correct.
Okay. Just here I have a question. Here you have your network here is trained in the second step. You are doing quantization for the activation function activations and for the and also for the weights, or for all the network, or just choosing, for example, just the weights, just the activations, or both?
To answer, we didn't quantize the activations, so yeah, quantize the feature vectors, which is the inputs of the NLP, and we didn't quantize, we didn't quantize weights or activations of the NLP at all.
Okay, and in both directions, in forward propagation and backward propagation, or just did you catch my idea?
I'm sorry, I didn't.
No, probably you should ask again your question, Mustafa.
Okay, for while training, you have the forward propagation and the backward propagation.
Yes.
Yes. So here, did you apply the quantization in both directions, or just in the forward propagation, and then you have or in the reverse way?
You can see from the paper that we only quantized on the forward propagation, and you use the, do you know the straight through estimator?
No, but
there's a technique that always be used when quantizing the model. So we also use the same technique here.
Okay.
So, okay, thank you.
Thank you very much. So once again, thank you for the presentation. So the next speaker is JJ Ning. So you can
Yeah, I'm
share
here.
your presentation. Okay, perfect.
Okay, thanks.
It's up to you.
So thanks very much. Hello, everyone. So I'm Zijining from IMT Atlantic, and I'm happy to present our paper entitled Enhancing Embedded AI-Based Object Detection Using Multi-View Approach. And this work has been done at IMT Atlantic in collaboration between Labstick and IRL Crossing Laboratories. So my presentation will be divided into several parts. First, I will briefly introduce our method and then introduce the dataset that we made ourselves. And then I will introduce our 3 experiments, especially the one that uses the multi-view approach. And I will conclude my presentation by a short summary. So we know that recent years, convolutional neural network has been used in the field of object detection. And in practical applications, we want to achieve very high accuracy while obtaining a very high operation speed. So this places a high demand on the computational power of the hardware. So when we want to implement such a CNN architecture on embedded systems, we usually need to make a compromise between speed and accuracy due to their limited computing power. So here, one way to solve this dilemma is the multi-view approach. So we want to build such a system using multiple cameras, and each one can view the object from its own angle. More precisely, we want to build such a network with several cameras, and each camera is equipped with an embedded system who can run the scripts locally. And we will later have a manager who can gather information. And multiple nodes will record the same object from different angles so that each node has their own different predictions on this object. So the goal now is to collect all the predictions and finally determine what the object really is. And each node, each camera should send such a string to the manager, including the class, the confidence, and the coordinates of the bounding box. So our method will have some advantages. First, we can get a system that runs in real time, because when using our method, we will try to use only small networks. And second, we will maintain a high accuracy at the same time, because we use the idea of collective intelligence. We have a manager who collects information, who collects everyone's predictions, and then gives the final result based on these predictions. Third, we can save energy. We can reduce energy consumption, because we know that for an embedded system, for example, Jetson Nano, Jetson TX2, its energy consumption is much lower than a PC equipped with a GPU. And finally, we can also protect the privacy, because this is the idea of edge computing. No image will be sent to cloud, so no sensitive information will be sent online. As far as we know, there is no pertinent dataset, no multi-view dataset which is pertinent for our experiments. So we decided to make a DIY dataset. So here is the idea. We have chosen some objects such as mug, wallet, and keyboard to make a controlled environment to show our prototype. And here is the result. As you can see, for this single scene, we have images from different angles. And finally, we got about 3,500 instances. So now with this data set, we can finally start our experiments. We firstly made an experiment to obtain some baseline value. And we use the YOLO V5 algorithm, which is a kind of state-of-art algorithm for object detection. And we launched 300 cycles of training on 5 different YOLO V5 models with different sizes, from nano, small, to medium, large, and extreme. We recorded the number of parameters, number of operations, and speed and accuracy. It's logical that larger models have more parameters which bring higher accuracy, but these larger models run more slowly. At the same time, we also recorded the energy consumption and memory usage. We noticed that the training of a larger model takes about 2 times the energy required to train a smaller model, and takes up a large amount of memory, like here and here. Just notice that due to the limit of GPU memory, we have to reduce the number of images treated each time. So in fact, here is about 4 times or 3 times the memory. So we think that smaller models are more pertinent to be implemented on an embedded system because they are faster to train and require less computing power from the hardware. And now I'd like to present our multi-view experiment. Here is the flow chart. Imagine we have a scene I, and in this example, maybe we have 4 images. So we will give each image to each camera as an input. So each camera will generate some groups of bounding boxes and predictions like classes and confidence score. We will firstly project each bounding box to the same plane, because we know that all the bounding boxes are not always on the angles of view are not always on the same plane. After this, we will try to merge the bounding boxes to decide which bounding boxes belong to the same object. Here is the idea. We will first project everything to the same plane and get such bounding boxes. We are inspired by the idea of no-max separation to develop our own algorithm to merge these bounding boxes. We will first remove the proposals with small confidence. So as you can see here, we have some bounding boxes with the confidence maybe larger than 0.6. And we will select the proposal with highest confidence score. So in this example, it's a big square here with confidence score 0.8. We will compare this proposal with all the other proposals and calculate the intersection over union. If this IOU is greater than the threshold, which means these 2 bounding boxes are too overlapped, we will remove the bounding box and merge their predictions. And we repeat. So here should be the result. We can see that all these 3 bounding boxes on the left are merged together at this big square one. So this bounding box should have 3 predictions, 3 classes, and 3 confidence score. So now we can start to calculate the accuracy, because we know that such bounding boxes are for the object 0 and those are for the object 1. We will first calculate the image accuracy, which means we will compare the output of each node with the ground truth. This is for the image accuracy. And then is for the sync accuracy, which means we want to compare the output of the whole system with the ground truth. And to decide what is the output of the system, we have developed some simple strategies. Just consider that we have a system of 7 cameras as shown here. And each camera gives a prediction for the object containing the class and the confidence. So we have defined 3 very simple strategies, and I'm sure that you can understand how they work from their names. Such as for the max strategy, it's just simply a winner take all. So in this case, it should be class 0 as output for confidence 0.8. And the average strategy is to calculate the average score, and this class 1 for this case. And the sum strategy is for class 2 in this case. So here's the result. We found out that no matter which strategy is used, we see a big improvement here on the accuracy for about 16% on nano model and about 9% on extreme model. The gap is more evident on smaller models. So we think that our multi-view approach can help smaller models to dig more details from the object. And after this, we made a camera position experiment because we want to investigate what is the impact of the positions of camera. So we built such a scene, including 8 cameras. And you can see 7 cameras here in the yellow circles, together with the camera who have taken this picture. And we will put objects in this red square, in this zone of objects. And here is the experiment. We have defined two groups of cameras. The first group in purple here, and this is a group of cameras who is able to observe around the object. And the second group, the green group, this is a group, the cameras here, they gather on only one side of the object. So we can see from the table of the results, although we see some improvement by using 4 cameras, which is the impact of number of cameras, we see that the purple group here, the purple group performs much better than the green group for the nano model, with a difference of about 13%. And as the model gets larger, the difference between the 2 groups is no more visible. So the impact of the position is more important for small models. And also by comparing the result from extreme model here with the result of nano model with multi-view approach, we are able to conclude that a group of better placed cameras could get a boost that previously required the use of a larger model, which means before we need to use an extreme model to get such accuracy. So to sum up, with our multi-view approach, we can build a system with 4 nano models whose precision, whose performance is better than a system with 1 extreme model. And our multi-view system, multi-view model, has only 1/10 as number of parameters and runs 20 times faster. And we think that our approach is of great interest to those who make prototype of object detection on embedded systems, because they can get reliable predictions before committing more resources on computing power. So that's all. Thanks for your attention. And if you have any questions, don't hesitate.
Thank you very much for the talk. Any question for GJ? Okay, I can start. So you have shown that you need some cameras, or many cameras, in fact, to get the different views.
Yes.
Is there any constraint in your experiment? Is there any constraint on your camera, on the synchronization of your camera? I mean, if it's static object, so probably you don't care about the synchronization of the different view. But if you have a dynamic moving of objects, do you care about the synchronization of the image you are looking for by the camera?
Yes, in fact, synchronization is truly a problem when we want to record something which runs really fast. And we have thought about this issue. And in fact, we made a small script to record everything, to write everything in a file, for example. And we will, when we want to get the result, we will read from this file to read this file with this time step to make the synchronization works. And this part is not presented here because in this paper, we want to focus on this approach. And the relative work about synchronization has been presented in another paper, in another work, in fact.
Okay. Yeha, you have a question?
Yes, thank you, Gigi, for your presentation. In fact, I have a couple of questions. First, can you please explain how you when you talk about reducing the power consumption or the optimization, can you show just me where this part takes place in your project?
Yes, it was made during the baseline experiment, in fact. And during this experiment, we recorded everything, including GPU power usage and GPU memory usage.
Okay, great. But here you show us, for example, it's a kind of one GPU. So if I want to calculate the total power consumption, so I need to multiply by because you are talking about multi-view cameras. So I need to multiply this by the number of your multi-view computing elements.
Yeah, that's it. We assume that if we want to use 4 cameras in our system, we will multiply the power usage by 4.
And this you assume that you have a linear relationship on your system.
Yeah, that's it. Because these 4 systems, they are individual. There are no no interaction between them, just communication.
Yes, and the communication also consumes, no?
Yeah, that's true. But we think that we are focused on GPU power usage here, because when we implement the CNN architecture, we think that its calculation on the network itself consumes much more power than the power for communication, for example.
Okay. Thank you, Ziggy. Concerning the speed, just the metric you have compared. So is the execution time on the GPU that it's per system, or?
This one?
Yes, the numbers at the end of the presentation. You have presented a number of in seconds. I remember.
Yeah.
Here 20. You say 20 times faster. So 2.6 second. It's your work achieved 2.6 second in what? In your system or even per camera or per system?
In fact, this time is the running time for each camera with a nano model, and we think that these 4 cameras, they run together. So the running time should always be 2.6 seconds. And if you want to launch an extreme model, for example, on one system, on one card, and the running time should be for more than 30 seconds. So this is how we calculate 20 times faster.
Okay. Thank you.
Thank you very much. We were supposed to have a 15-minute breaks, but as we are late, so I suggest to have at least 5 minutes and be back in 5 minutes. Is it okay? Okay, fine.
Yeah.
Okay, 5 minutes. Be back. Thank you.
So, Frederick, I will take the share of this session, and we can probably.
Yes, I think we can hear Ken.
Ken. I cannot hear him. Yes. So our first speaker is Weiyan Chang. So probably you are here. Hello. You can probably stop sharing, Frederick.
Yes. Someone has a microphone open.
No, there is only you, me, and the speaker.
Hi, can you hear me?
Yes, hello. So probably, Fred, you can stop your sharing, or on this is not you. No, this is you, yeah.
No, it was me.
Yes. Okay.
You see my
We can
slide?
see your slides, yes. Yes. So if you want, you can start.
Okay. Hello, everyone. My name is Weiyan Zhang, and I am a researcher at a German Research Center for Artificial Intelligence. My topic today is ANN-based performance estimation of embedded software for RISC-V processors. And my presentation will be given in the following 4 aspects: background, our approach, experimental evaluation, and conclusions. Some advantages of RISC-V instruction set architecture are listed here. It is completely open and is freely available to academia and industry. There are 2 variants, RV32 and RV64, which provide 32-bit and 64-bit user-level address spaces, respectively. The base integer ISA can be extended with optional extensions. For example, the standard integer multiplication and division extension can be extended, and it is named as M. Then the new architecture is RV32IM. It is supported by GNU compiler connection and the Linux operating system. Additionally, the ecosystem is growing rapidly. It is very important to do embedded software simulation at an early stage to explore the design space efficiently and to reduce time to market. There are a variety of simulation techniques, from very fast functional simulator without any cycle information to very slow RTL model with cycle information. The performance of the virtual prototype is between them, and we are motivated by the huge difference between them and trying to find a fast and accurate approach. Our approach can be divided into 4 steps. Firstly, a comprehensive training software set and new software are compared using RISC-V GNU toolchain to generate the executable files. Then, secondly, a processor model is used to execute the executable files of training software to generate the runtime log. Based on this log file, we can generate the training data set. Then we apply the artificial neural network to the training data set, and the hyperparameters are tuned and the model parameters are optimized. After obtaining the predictive model, the executable file of new software is executed on a functional simulator to generate the instruction information log. The dataset is generated based on this instruction information log. Then the testing dataset is given to the predictive model to estimate the cycles. There is a brief introduction to my artificial neural network. The inputs are the numbers of each instruction, and the output is the number of cycles. There are several hidden layers between input layer and output layer. The value in each neural and the cost function are calculated in a feed-forward process, and the width and the bias of the network are updated in the backpropagation process to choose the hyperparameter, such as learning rate, the number of hidden layers, the number of neurons in each hidden layer, and so on. We define a search space for each hyperparameter in order to find the best value. All of our experiments were carried on Linux system and an AMD processor. We use the RISC-V VP as our processor model and the RV8 as our functional simulator. The artificial neural network is implemented in TensorFlow for testing. Our testing software are from InBench, TacoBench, and RV8 Bench. And all this software and the benchmarks are open source. To measure the model, we calculate the absolute percentage error for each test software. We also calculate the mean absolute percentage error for overall benchmarks. And in those two equations, the y hat is the estimated number of cycle, and the capital K is the number of our test benchmarks. We considered three architectures. Those two figures show the results for RV32I and RV32AM in terms of absolute percentage error and speed up. The x-axis is 10 benchmarks and the average value of them. We compared our model with the other approach, which mentioned in the paper 21. And the black and the green bars represent the results that represent the absolute percentage error of our model and the paper number 1. And for overall benchmarks, our model outperforms the approach from paper 21. And for overall performance, our model achieves the mean absolute percentage error with 2.1%, but the results from paper 21 is 3.7%. And our model reaches a speed up to 3.7 when we compare our methods with the RISC-V VP. And for RV32AM, this architecture, we also compare our method with the paper 21, and it shows that the mean absolute percentage error for our model is only 2%, and the mean absolute percentage error for paper 21 is 5%, and our model achieves a speed up to 3.9. For architecture RV32IC, we don't have any comparison results because in paper 21, there is no information for this architecture. So we listed our results in this table. And our model achieves a speed up to 4.41, and the mean absolute percentage error is 2.64%. In summary, a level ANN-based approach to estimate the performance of a given embedded software on RISC-V processor is proposed, and we consider 3 architectures: RV32I, RV32AM, and RV32IC. We utilize the ANN-based models and a functional simulator to estimate the number of cycles. We validate our predictive models using standard benchmarks in terms of simulation speed and accuracy. Thank you. So if you have any questions, feel free to ask.
Thank you for this nice clear presentation. Questions from the audience? Yes, Fred.
Yes, everyone. Thank you for the talk. You did not mention any limitation for your work. So you said at the end that you had quite good results, but does it work for the application level, for middleware level, for low level software? So is it similar for all kind of software, or is it just for some, I don't know, application or specific stuff?
Yeah, it works for almost every embedded software because I created the training software by my own. So, and the testing software are benchmarked. So the software between training software and testing software are totally different. Yeah, and this is also one of our goal to make them different.
Okay. So okay for the benchmark. So it's more on the application level, but have you seen some limitations you did not present in your talk?
Actually, not every not every benchmarks shows very good results. For example, you can look at the architecture RV32AM, the first benchmark, or for the first benchmark, the error is around 4.5%.
But are you able to explain why?
Yeah, and if the error is very large, the reason is that the testing data set is out of range of the training data set, because for our training data set, it is impossible to cover all kind of situations. So there are some limitations. Yeah.
Okay, thank you.
Welcome.
Thank you. Other questions? Just can you go back, please, to the one of the first slides where you talk about design space, space exploration? Yes, search space. Yes. And so this was your search space, and finally your approach. You explore all of these for each benchmark, or how it's done?
I can show you the models. So I have 3 architectures. So I generated 3 models, and for each architecture I have 1 model. And after after I use the random search algorithm to find a best model, and for the first predictive model, I got the best value for each hyperparameter.
Okay.
Uh,
Okay. Thank you. And for your data set, what's the size of the data set for
the first architecture, the data set is 167 times 40.
Okay.
Mm.
Okay, thank you.
Welcome.
Other questions?
So I have one more question. So actually, Frederick already mentioned this application-specific thing, and we all know that RISC-V is useful for this domain-specific accelerator. So in this case, if you want to, extend your data path for some application-specific acceleration stuff, then in this technique, would you require retraining, or do you need to train the entire model over again? Or do you just reuse this model?
You mean if the new software is from accelerator?
Not only about software, but RISC-V support this, data path extension for application-specific thing, right? So my question is, in this case, how much part of your model can be reused? That's my question.
So you mean new software?
Yeah, possibly software, but possibly maybe we can extend the data path a little bit. RISC-V support this kind of extension, right?
If you want to extend your data set, then you have to retrain the neural network to retrain a network.
Mm-hmm.
And
Got it.
Yeah.
The question is about if you extend the instruction set, the instruction, if you add some specific instructions to your architecture, if you add some specific instructions, the application specific instructions, should you retrain?
No, we don't need to retrain. For example, if we consider only one architecture, it's RV32i. It contains 40 instructions, and if you, no matter which software you executed, then you can obtain a trace, and from the trace that the instructions are belongs to those 40 instructions. You just need to calculate the numbers for each instruction.
Okay, got it. Thank you.
Thank you. Other questions? No, I think we can. So thank Wayan again, and go to the next speaker. So our next speaker is Arthur Vianney from Grenoble-Alpes University.
Yes, I'm here.
Hello, Arthur.
Hello, I will share my screen.
Yes, please.
Yeah, is it okay?
Yes, perfect.
Okay, so hello. I'm Arthur Vianney from Teamalab at Université Grenoble-Alpes, France. And I will present you a work which is done as a collaboration between the Teamalab and the Calray company, which is a French fabless semiconductor company that build many core accelerators. This work is about a second level software cache coherence prototype in the context of many core accelerators. So first, I will introduce you what many core architecture and some basics about cache coherence. And when all the bases will will be exposed. I will introduce you our work, our proposal, and finally I will discuss the advantage, the disadvantage, and what this protocol helped for cache coherence prototyping. This work targets the Calray MPPA processor. It's many core accelerators from Calray, but our conclusion will apply to any many core architectures. So many cores accelerator is a type of processors that is made up of a large number of core and from 100 to 1000 core. Such large number of core put a lot of pressure on the memory system, and to handle it, many core processors adopt cluster architecture where computing cores are grouped into clusters. Each cluster have a cache, a scratch or a scratch pad memory that is shared with all the core of the cluster, just as in this figure on the left. So in this figure, PE are computing core. Each core have a private level 1 cache, and they are grouped into clusters. And each cluster have a level 2 cache. This architecture is particularly efficient regarding highly parallel workload. And this may be used for really parallel workloads. So having many core and many cache is really good for parallel workloads, but it exposes the memory to cache incoherence issue. So a cache incoherence situation is when multiple cores see different versions of the same memory because of cache that contain concurrent version of the same element. In this figure, you can see that some cores see the value x as 0 and others see the value 1 as 1 because of the cache. And this situation has to be avoided since it makes it harder to develop a general purpose application. So it's lower programmability. To prevent this situation, a cache coherence protocol is required. This can be achieved and it's commonly achieved using the single writer, multiple writer invariant. So it's illustrated in the figure on the left. The arrow represents memory access, and the C1 and C0 is our core 1 and 0, and there are cores that see the memory as cache coherent. So in the first figure on the left, this is a totally legal situation. Every access is directed toward an address that is only used either as read-only or is accessed by a single core. But on the second figure, this is an illegal situation since both core 0 and core 1 access the same memory address with write permission. So it breaks the single writer invariant. Using this invariant, the job of the cache coherence protocol is basically just to ensure that no data in the cache could be accessed by two actors with write access. In other words, using this invariant, the cache coherence protocol only need to manage access permission on addresses. Note that the single writer invariant is not the only way to enforce cache coherence. It's just the most common way. And in the end, cache coherence is a trade-off between simplicity and programmability. So you will not always use it, but it will be interesting. So what about many-core architecture and cache coherence? So it's a well-known problem because as the number of core increase, the cache coherence hardware become more complex. Therefore, it's harder to verify. It's become expensive in surface area, and in latency, it's harder to verify. I always say. Also, many core workloads, which are highly parallel workload, generally do not rely on cache coherence, since cache coherence serialize memory access, and so you don't want to serialize your memory access. So many core workloads are written in order to not rely on cache coherence, meaning that cache coherence have little to no benefit in many core workloads. The complex hardware global cache coherence on many core accelerator is a pretty bad trade-off. The common solution regarding cache coherence on many core accelerator is then just to fully disable the cache coherence. However, no cache coherence means that generic software that rely on cache coherence will not run properly on this accelerator, like libraries on some framework or operating system. If you need one of them, you have to rewrite it on or part of it for the many core accelerators. Our proposal is to at Calray we have implemented a first level of cache coherence, but a simple one on the many core architecture. So basically, our proposal is to re-enable global cache coherence on many core accelerator, but using 2 levels of cache coherence. And both protocols are really different. Our intention is to investigate the other trade-off and to find one trade-off that better match many core workloads needs. So as I said, at Calray, we try to build a first level cache coherence, which is a very simple one in hardware, but just within cluster, as in the figure, and this figure. This cache coherence protocol is only local to one cluster. So clusters are coherency island, meaning that every cluster, every core of the cluster see the memory as cache coherent with other core of this cluster, but it does not see memory as cache coherent with other core from other cluster. So yeah, and this allows us, for example, to run Linux. To implement this in hardware, your technique is to rely on write full cache. So a write full cache is a type of cache that is not a write byte cache. So first, a write byte cache is a cache where every write access is done directly into the cache. And to make memory access visible to the other cache, to the other core, you have to write in back the cache line to the memory. While with write full cache, every access goes directly both to the cache and the main memory, so it's directly visible to all to every core. So this way, the main memory always contains a valid up-to-date data, and this means the cache coherence protocol do not have to deal with memory ordering. And so to implement the cache coherence in hardware with write full cache, you just have to propagate an invalidate signal to every core that shares this line. So it's work, but it's limited to a smaller number of cores. It does not scale at a big number of cores, so we can just apply it to the one cluster. So we need a second level of cache coherence that will unify every coherency island. So to do that, we rely on on memory management unit, MMU in short. So every modern processor integrates an MMU. It's allowed to isolate process for security and programmability reason. This way, user application only manipulate virtual addresses and do not need to worry about real physical memory behind it. The role of the MMU is to translate virtual addresses to physical addresses. This translation is done as the granularity of the memory page, which is about 4 kilobytes in size. And during this process, the MMU also check permission of the user application on this memory address. So this is how it works. This figure illustrates how it interacts with the rest of the system. When a user application, so represented in the left, perform a memory access, further access will go through the MMU, which is the TLB in the figure. The TLB from the MMU will look up for a translation a translation for this virtual address, and it will also check page permission regarding this address. If there is a match, then it will perform the memory access. If it fails, it will go to the page walker, and the page walker will check if there is any update for this. If there is any update to do on the MMU, and we basically have to replace this page walker with our own protocol to make our software cache coherence protocol, since the cache coherence protocol just have to check for permission. So in the end, we have a two-level cache coherence protocol. One global cache coherence on software and one one global cache coherence in software and one local cache coherence in hardware. So regarding prototyping at Calray, this cache coherence protocol will help us to prototype global cache coherence protocol and evaluate your future workload. Because we have to know if it will better fit for a software cache coherence protocol or an hardware one. It's a complex question to answer, because it's really about finding the best trade-off, and there's many things that count as the hardware complexity, and if we need cache coherence for any kind of application, and what's the cost. Thank you.
Thank you, Artur, for the nice talk. So we have time for a few questions from the audience. If there is no, I can start myself. So in terms of, can you go back just to the previous slide?
Which one?
Yeah, this one. No.
This one.
Yeah, this one. When you say no need for extra hardware, but you said that you need to have, I mean, local. You have locally inside the cluster. You have to add some central hardware for cache.
That's a piece of hardware we already have, because some application rely on this within the cluster. It's allow us, for example, to run Linux on. So since it's very cheap, it's like no extra hardware, but yeah, it's.
Yeah, no extra hardware with respect to, I mean, typical.
But even it's not a lot of hardware for this protocol, as I said.
And I haven't seen that much some quantitative results. I mean, what's how you make validation and experimentation? You have used the Curly platforms, the many core platforms from Curly.
we use the hardware from Calray, and yeah, we do not present any result since it's an ongoing works, and since it's a new feature. So yeah, of course, maybe it will cost a lot. No, not a lot. It will cost some performance, but it will allow us to run our software on every core of the platform.
And having so the idea here to have this intra cluster cache coherence, and you assume that between clusters, you assume that there is no cache coherence between clusters, right?
Yeah, because it's the costly one, the one that talk about between clusters.
Okay. Yeah, thank you. Questions from the audience? So next step, what will be in this regard? What will be the next step?
You mean in this work?
Yeah.
Yeah. I mean to find some results, and also there's a mini optimization that it's possible. For example, in this slide, say in the left, there is an initialization cost as every when you run your application, you load every code. So so every page of memory that needs the code will trigger the cache coherence protocol. But since the memory that is marked as a code can be mapped directly as a read-only page.
Okay.
So you can save a lot in the initialization and things like that.
Okay.
Also, you can just disable the cache coherence in some memory, so it will save time.
Okay, and for my curiosity, if there is no cache coherence, if it is disabled, as it's as you have said initially, so how it's done for operating system like Linux, etc., to run on this platform?
Yeah, that's why we can only run Linux in one cluster, because there's cache coherence. Just that's the problem.
And this is the situation today. I mean, it's not like
yeah,
this.
it's the situation today.
Okay. Okay. Thank you again, Arthur.
Thank you.
Any other question from the audience? No. Okay. Thank you again. So we can pursue to the next slide. If you can please stop sharing. And our next speaker, is here.
Yeah, I'm here.
Yes, hello, Nino Roma. So please, Martin Rosado.
Yep.
So please, if you can share your slides.
Right, so you should be seeing slides.
Yes.
Right, so thank you for joining me. So I'm Martin. I'm a master's student at CERN and at the University of Lisbon. So it's my pleasure to share with you the work I've been involved with, which is the testing of an FPGA-based control systems for ASICs that will be in use in a detector, in a particle detector. So before we go to the work, I will provide some context about the overall system. Then I'll talk about the prototyping system that was developed, and finally I will conclude with some results. So first, starting from the beginning, CERN hosts the world's biggest particle accelerator, the Large Hadron Collider near Geneva, and at this accelerator, protons are accelerated to almost the speed of light and collide in 4 points. At each one of these points, there is a detector. which measures every collision that happens. And this work contributes to the CMS detector, the compact muon solenoid. So the LHC, the accelerator, will be upgraded in the next years, and collisions are expected to increase tenfold. And of course, this upgrade poses significant challenges to the detector technology. So several detectors will need to be replaced due to performance loss. And new detectors need to be developed. One of such detectors, it's the high granularity colorimeter, HGCAL, which will replace the end cap colorimeters of CMS. So it's a high resolution colorimeter that provides high precision measurements through around 6 million channels. And so there is the need to use a complex readout chain, and this chain uses a lot of ASICs, around 150,000, using radiation tolerant technology. So this readout chain is separated in two zones, the backend and the front end. So the ASICs perform first level of data processing on the front end, and then convey data to the backend, where around 100 FPGAs do further processing and also control the ASICs on the front end. So each FPGA processes around 1 terabyte per second of data and needs to control 3,500 ASICs. So the purpose of this work is to prototype a control system to be implemented on every FPGA to control the front-end ASICs. So this control system receives, it's called the slow control, and receives slow command data from software running on a multiprocessor system on chip, hosted on the same board as the FPGA, and then needs to propagate this configuration and control commands to the front-end ASICs. There are two layers here. So the first one is the one that is directly interfaced by the slow control, and this layer involves 750 ASICs around per FPGA. And there are two different ASICs here, the low power gigabit transceiver, LPGBT, and the gigabit transceiver slow control adapter, GBT-SCA. Once slow commands reach these ASICs, they are propagated further down the chain via I2C to all the rest of the 3,500 ASICs. So to do the slow control, we use the LPGBT protocol and the HDLC protocol. Each one is associated with either the LPGBT or the GBT-SCA, and we don't use all of the bandwidth of these protocols. So for example, we only use 80 megabit per second on the signals to transmit slow control data to the front end. So this is the architecture of the block that needs to be prototyped. It needs to interface the software and the front end of the detector. On the software side, it will get it communicates with software via two AXI interfaces. It gets data from an AXI full interface that stores this data on buffers and receives control signals that control registers through the AXI Lite interface. So the procedure to use the block starts on the software. So software transfers data into the slow control block, then the slow control block gets activated and processes the transactions, sends them to the front end. The front end gets the transactions, generates a reply, sends the reply back to the slow control block. Slow control gets the reply and stores it on buffers that then the software can read. And this architecture is based on cores that can execute independently to get some parallelism. Each core is associated with the LPGBT protocol or the GBT-SCA protocol, and it's composed of three main components. One is a transactor, which is a simple state machine that interfaces the memory buffers, gets the data and decodes it, and controls all data flow inside each core. Then we have the engine that gets the data from the transactor, translates it into the respective protocol, and sends it to a multiplexing circuit that should route the transaction to the target ASIC. This architecture allows to take into account software constraints, for example, the number of threads able to drive each core, and it needs to interface the front end with the 2-bit stream signals. So unfortunately, the final detector hardware is not available yet. So both front end and back end had to be emulated at system level during the prototyping. This is the setup that we used. On the front end side, we used the VLDB Plus and VLDB development boards. These are development boards developed by CERN to allow the prototyping of these systems with the final ASICs to be used on the detector systems. And on the backend, we use the Xilinx ZCU102 development board, which allows to use the same UltraScale Plus technology Linux framework in the AXI interface that will also be used on the final detector. So inside the FPGA, we have, of course, this slow control block, which is connected via AXI to the processing system of the Zinc device. And then we connect the slow control to an LPGPT link hardware block, which encodes full LPGPT frames. So as I said, we don't use the full LGBT frame, only a small part to guarantee bandwidth to do the slow control operations. Then the data generated from the LPGPT link is connected to the multi-gigabit transceiver that is then connected to the front end. On the software side, we use the CentOS 7 Linux distribution on the processing system. On top of CentOS 7, we use the Python script that allowed us to test and validate the AXI interface connection, LPGPT and GBT-SC connections. Apart from the replies that we read from the slow control, we also used LEDs on the development boards to verify that the transactions were successful. After we got a reliable connection, we then stress tested the system, issuing around 10 million transactions to each core. And these transactions allowed to roughly estimate the configuration time for all of the detector in the order of 1 minute. It meets the required performance, but to make a more accurate estimate, there is the need of a final software architecture that is not available yet. The slow control, after this validation, will be ported and used in different test systems and, of course, in the final detector. And the test system, as of now, it has a relatively low resource utilization. So there is room for broadening of its use to test other aspects of this big detector. Thank you. Do you have any questions?
Thank you, Martin, for this nice talk and impressive prototyping system. Questions? Yes, Frederick?
Yeah, I just would like to know if it's a new system and you build something new, or the system already exists and it's just an update with new technology.
So what system are you referring to? The detector is being built. So the detector for sure is new. The slow control block, so if I can, maybe here. The slow control block was already developed, but it needed to be tested and validated. And the test system is a new system. So it was developed from scratch.
Okay, I have seen also at the end of your presentation, you give some result on the percentage of the use of the resource on the FPGA. So it's, I would say, quite small. Why do you use a huge FPGA just to put, I don't know, few percent only on this architecture?
So
is there a specific reason for that?
Yeah, so one is the shared technology with the final system FPGA. So in the final system, we are using a big FPGA that uses UltraScale Plus technology, and using the same FPGA technology here facilitates port slow control between systems. And also this board is being used on other prototyping systems, so it's easy to expand this system to test other things and integrate new components. So in that aspect, it's an advantage to use the same board and to have available resources.
Okay, thank you. It seems to me it's a huge, huge device. And,
also, so there is another aspect that if you see in here, in this test system, we are only interfacing one LPGBT and GBT-SCA. So once we need to test more ASICs at the same time, the slow control block will also grow in complexity. So we didn't instantiate all slow control blocks. So if you see here on the architecture, in the final system, we intend to instantiate 16 of each core. We only used one because we didn't need that many as of now.
Oh, yeah, okay, thank you.
Other questions? You have said, yeah, at this slide, you say that more accurate estimates require a final software architecture, which is what do you mean by this? Well, what's missing in terms of software development to have the full accurate estimation?
So if you come back here, each of these ASICs has to interface other ASICs via I2C, but this is only the slow control network. So once we start taking into account data connections and all of these things, so there are different architectures on the front end. There are not yet a defined set of configuration for all of ASICs. For example, some of the Econ ASICs that you can see here are still under development. So it was not developed yet a data set with all of the configurations to be transmitted to the front end. So this software doesn't exist yet. The software that we use now, it's only to test that we are able to interface the ASICs and not exactly to configure them from the ground up like it will be needed on the final detector.
Okay. Okay, and I mean, probably I have missed this at the starting. So the configuration, it's done. This configuration of the ASICs is done at the start at each experiment. That's just new experiment.
Yes. So every time the detector is powered up, all ASICs need to be configured. And also between runs, there might be the need to configure only some ASICs, maybe not all of them, but so configuration might be changing, but it's not expected for it to happen very often.
Okay, so we can tolerate, I mean, a few minutes of time to configure.
Yes, exactly.
Okay. In all cases, it's really impressive. I have never seen these numbers of ASICs and FPGAs. But yeah, and there is in terms of latency, there is no constraint for this. I mean, for this in terms of latency, even throughput. I mean, there is no big constraints on this because it's only to configure the ASICs before running.
So there is not a hard constraint, but if the configuration takes too long, it will start to increase the dead time of the detector. And while the accelerator is running, this translates into loss of data. So it should be in the order of a few minutes, not more than that. So it's not a hard constraint if 2-3 minutes, but a bit more than that, it starts to be a problem.
Okay. Thank you. Thank you again, Martin.
Thank you.
So this ends our second session. We can have a 5 minutes break, and if you agree, and then starts again. Yeah, in 5 minutes. Thank you. See you later.
Jacob, you are the first speaker in this session 3.
Yeah, should I start? Are we ready?
No, I think we should wait 1 or 2 more minutes.
Sure.
Okay, so I suggest to start again the last session about analysis and trade-offs in rapid system prototyping. So the first speaker in this third session is Jacob Wenzel. So I will stop sharing my screen and you can start.
Yeah, hello, I'm Jacob Wenzel and welcome to my talk on our paper, Automatically Restructuring HDR Modules for Improved Reusability in Rapid Synthesis. With ever-increasing FPGA device size, improvements in compilation time have not kept up with the device size, and such compilation takes longer and longer. And the main reason is that we always recompile the whole design from scratch, leading to a very non-interactive workflow. One approach to speed things up, which is quite common in literature, is to use pre-implemented modules. So when we have a design, we take all top-level instances separately and pre-implement them. Here we have no hierarchy support, we only take top-level instances. And then we can assemble the design out of these pre-implemented Lego blocks. So those pre-implemented modules are created in isolation. They're not as optimal, but we only have to do this pre-implementation once. So we trade some clock frequency for faster turnaround time. Why can we even do this? Well, FPGA fabric is regular, so modules can be relocated after being created at some specific place on the fabric, and we even can instantiate the same module multiple times. A tool to interface with Vivado is RapidWrite. It's an open source tool developed by Xilinx, and it can read and write Vivado checkpoints, all those .dcp parts here, at different phases in the design process. It is a general purpose library and also includes, as an example, one such pre-implemented modules flow. A problem with existing tools is that they all have different input formats, and most even have a split between the top-level design and the IP core implementation. So if your design does not have the same split, does not conform to the tool's requirements, well, then you're out of luck. You can't use this tool. We want to make things better by having our own tool that uses Verilog code as input and treats IP cores and top level identically, and thus is kind of a front end for existing pre-implemented module flows. So the goal of our tool is to restructure the design such that it's good to use in a pre-implemented modules tool where every top level instance becomes one such module. So our top level instances must be suitable. And one problem is when we have Verilog parameters, when we even just change one parameter in the whole set of parameters of a module, we have to build the whole module again, a new pre-implemented block with just this one change parameter, or the whole block has to be recreated. Now the question is, can we do better? In fact, in the past, we wrote another similar tool, RapidSorg, where we supported replacing equality checkers and hierarchy parameters after the block was built. However, users had to tell our tool,
about the specific instance where one such thing was located. So our goal is to do this automatically. So we want to identify parameters that only have a small effect and move those parameters to a separate module. As an example, here we have a child module with two parameters in orange and green. And here they are together in a single module. And the goal is to have a restructured thing like on the right, where the affected area of each parameter is separated into separate modules. Of course, here we have more of a 50-50 split between both parameters, but in actual designs, we aim to extract parameters that only affect a small area compared to the whole module. In order to not reinvent the wheel, we use an existing Verilog parser, namely EOSYS, which has a plugin interface, so we can interface to it easily, and it can also do formal verification, which allows us to check out transformations for correctness. Looking into the individual steps of our tool, we have quite a number of them. In dark gray, we have parse code, which is just the regular EOSYS parse. The parses in light gray are existing in EOSYS, but we had to tweak them slightly to make them fit for our goal. And the white parses are completely new. We start after parsing by collecting the parameter info. Then we elaborate the design, generate intermediate representation, then analyze connectivity. Then we want to restructure the design. So we have to decide on a new structure. This is more, this is not yet finished. So creating a whole restructuring metric is kind of future work. After the structure is decided on, we have to apply it. And right now, because this restructuring algorithm is not yet, this decision algorithm is not yet finished, we just extract all the parameters that we can extract every time. Let's start with collecting parameter information. First roadblock was that in Verilog, we have parameters and we have local params. In normal synthesis tools, the tool doesn't care if you use a parameter versus a local param. However, in our tool, this will make a difference because we move parameters to separate modules. So a normal code, developers can just use parameters and maybe don't even know that local params exist, but this is a problem for our tool. So we have to do something about it, and that is to recognize that a parameter is locally used only and could be a local param. And we developed a simple metric, which is that true parameters tend to be declared at the top of the file, while locally used parameters tend to be declared further down, and then we can just convert them to local params. We took a huge set of benchmarks, which included the Titan set of benchmarks, VTR benchmarks, EOSYS benchmarks, and SparkNFC SOC kit modules, which in total were 7,300 different Verilog modules containing 144,000 blocks. And by blocks, I mean all the contents of modules, which are other module instances, assign blocks, and always blocks. And they had around 15,000 parameters. When running our heuristic on those parameters, we have quite good results matching the actual usage, and we only have small number of cases where parameters were used globally, but a heuristic thought they were used locally, but that's no problem because when the parameter actually gets overwritten, we can just revert our local param conversion, and around 10% are heuristic thinks they're globally used, but they are local. Well, that's just a missed optimization opportunity we have to live with. So around 10,000 parameters are remaining at this after this step. Then we just start with all parameters being marked as we could extract them, and then just have a number of things that make them non-extractable, which is being used in generate ifs or generate loops, because they are just too complex to be able to extract them, or that they are too tightly coupled. Here we have number of parameters that are just always used in tandem, and there we can just can't really do anything about it. For more details, I would ask you to look at our paper where we have written this algorithm in detail. Let's now look at how we actually apply the new module structure with the same example as before. And we do this in 2 steps. First, we inline all the contents of the child module into the parent, and we prefix all names with the name of the now inline child module to prevent any name collisions. Afterwards, we outline, which is just the reverse of inlining the 2 parts of the module, and then we are finished. We have the 2 separate parts of the modules. With the same benchmark set, we have those results where we have 2,000 extractable parameters and also 2,000 extractable blocks, which gives us 1 block per parameter, which sounds quite nice. All the parameters we identified are always contained just in 1 block. However, those numbers are don't show the true distribution, and in fact we have some modules where we have a huge number of parameters only used in a single block, which then is a big module, and we have other modules at the other extreme where a single parameter is used in many blocks. Both of those are not conformant to our goal from the beginning, where we want to extract parameters that are only used in a small number of cases. So we had to restrict the actual number of blocks per parameter where we want to extract the parameter. And we did that by limiting this number from 0.75 to 5 blocks per parameter. Those are our finished numbers. And here we can see that by extracting just 1% of all blocks, we can extract 10% of all parameters. So 10% of all parameters are just contained in a tiny fraction of all instances in this design, which is quite good of a result. So to conclude, we were able to convert locally used parameters to local params, detect extractable parameters, and then restructure the design to extract them. And extracting 1% of all blocks accounts for 10% of all parameters. As an outlook, as I said, we want to integrate other decision metrics for creating a full restructuring module flow. And also we want to handle tiny extracted modules, especially when we then place the modules on the fabric. Thank you for your attention, and I'm open for any questions.
Thank you, Jacob, for the presentation. Any question?
Sure, I can ask one, Fred.
I can.
Hey, thanks, Jacob, for the very interesting presentation. You mentioned the benchmarks that you use for testing. Did you look at using the benchmark set Kois++?
No, I'm not aware of them.
Okay, so that was a recent benchmark set that was published for the VTR flow. That's more circuits that are AI-based ones.
Okay. Could you spell the name of them?
KOIOS.
Could you put it in the?
I can
in the chat.
I'll look it up and verify the spelling, and I'll put it there in the chat for you to look at.
Thank you.
right after the.
Definitely have a look at them.
Yeah. The other thing I was going to ask was, so whenever you're making decisions in the VTR flow on the earlier stage, one of the bigger tricks is the trying to understand if you're making a good or a bad decision based upon what the impact is at the end. So definitely resynthesis is a nice thing, but what's the penalty in terms of the final circuit that gets built in terms of the quality of the result?
Yeah, there definitely is an impact in maximum clock frequency because we have a longer routing length between different modules. And that, in fact, is one thing I'm trying to improve in this full restructuring flow, where I'm looking at whether there are any only combinatoric paths that fully pass through a module, where we have this penalty applied twice. So this is a thing that I want to avoid by restructuring the modules.
Yeah. So what were you seeing as the penalties for area and for frequency by using their structured?
For frequency, it was around 30%.
And for area?
In area, I'm not sure. I would have to look that up.
Okay. And then my last question would be around the FPGA architecture. I assume with this flow here, you're looking at targeting a generic FPGA architecture where it's just all soft logic and not one where you have a hard logic, part of the fabric where the position of the hard logic and things like that start having a larger impact on structured versus unstructured Verilog.
So we're looking at targeting Xilinx FPGAs, and I think this is a question of module size. When you have two large modules, you find that you use combinations of a logic that only exists in a few places on the chip, and while you use smaller modules, you find that they occur more often. However, the smaller the module, the more connections between them you have, and this is also a trade-off.
Okay.
Okay. Thank you. Thank you, Ken. I suggest to move to the next speaker. So thank you very much, Jacob.
Yeah, thank you for having me.
So I don't know who is the next speaker.
Should be me. So
okay.
Should I take over the screen?
Sorry.
Just a second. Somehow I can't see the Zoom session.
And don't forget to put in the chat the name of the benchmark and maybe the link or something like that.
Will do.
Yeah, somehow I think I have to log on again. It showed on a different screen. Just a second.
Okay.
Okay. Now I can see the Zoom menu again. Let me start sharing.
Not yet, but it should arrive. Okay.
Can you see my screen
Yep.
yet?
Yep.
Okay, I may have to.
Yeah.
Change the screen
I think it's
again.
the presentation mode here.
Yep. There we go. Unfortunately, you can't see my camera now. This is why I originally changed the setup.
Okay, no worries for that. So this we can see your slide and it's in full screen. So perfect.
I will show up for the questions later. So, hello everyone. My name is Gabriel Rutsch, and I'm working in Infineon Systems Methodology Department, and have focused on AMS emulation on FPGAs for the last roughly 4 years. Today, I will show you a framework that enables systematic analysis of mixed signal applications that are run on an FPGA. Digital transformation has an impact on our daily lives, and specifically the way how we interact with the environment. From a product's perspective, AMS blocks and embedded software play a fundamental role, and specifically AMS simulation throughput plays a key role when developing these kinds of products. FPGA emulation of AMS applications has shown benchmark simulation throughput. Nevertheless, this is still considered a niche topic, and in this presentation, I would like to emphasize on one of the reasons why that is the case. I will first give an overview of commonly used AMS analysis platforms, then show you some previous work, mention the design goals we pursued when developing this framework, show you the framework, and also how it is used in real-life experiments. So the most commonly used platform to analyze AMSN applications are CPU-based. You could take any kind of SPICE solver here or MATLAB Simulink. You can also use a hardware-in-the-loop setup where part of the application is represented as discretes and the remainder is, for example, mapped onto the programmable logic of an FPGA. You can use a proprietary emulator like Zibo or Palladium, do the analysis post-silicon in a lab, or use an FPGA. As I mentioned before, what we're really looking for is simulation throughput. And there, the most common platform, which is CPU-based, is lacking. Therefore, we started looking into FPGAs. And here, one of the biggest gaps is the analysis capabilities of AMS applications. Whereas analysis capabilities I consider as, on the one hand, the capability to understand what is going on in the device and the test, and on the other hand, also the capability to control the execution of an experiment. This is what we would like to focus in this presentation. So let's have a look at related work with respect to analysis on FPGA designs. In the past, it was mainly focused to reduce FPGA technology-related shortcomings, such as I/O-related bandwidth or latency limitations, improving visibility of purely digital designs, eliminating the impact of auxiliary instrumentation on the execution of the device on a test, and also reducing the necessity to synthesize again after changing some configuration of the instrumentation around the device on a test. What has not been addressed, though, are challenges specifically related to the analysis of analog aspects like detection of limit, crossing, slope, period, or the injection of arbitrary stimuli and noise. Looking at FPGA AMS emulation, this is fundamentally well explored, but as I mentioned before, rarely used in practice. Research focus here was to further improve simulation throughput, optimizing the trade-off between FPGA resource utilization and simulation throughput, and the capability to conduct entire regressions of AMS applications on the FPGA. The main instrumentation that was used to conduct these experiments was leveraged from purely digital designs, and only for this one specific analog aspect of interest in this experiment, a custom single point solution was developed, like a very custom sine wave generator. Still, there's a lack of an effective and systematic way how to analyze AMS applications on an emulator. Those two topics we will focus on. The main goals we pursued when implementing this methodology was on the one hand to enable an interactive way of working. So both of the main instrumentations which we developed, a function generator and an oscilloscope, are both runtime reconfigurable and reroutable. On the other hand, we wanted to assure seamless integration to an already existing framework to host FPGA emulations called NSMod, from which we could leverage a significant amount of automation, also instrumentation. We wanted to assure that resource utilization on the FPGA is as minimal as possible, and therefore we implemented the instrumentation through generators, which are configurable. So you're really able to customize your instrumentation to the experiments of interest. We made use of mux structures to reduce routing resources. And also we made sure that the cores of the main instrumentation blocks we built are generic to be able to repurpose them during runtime and reduce the total amount of cores that are needed. Further, we assured that the impact on simulation throughput is as minimal as possible by employing an already existing framework to generate functional models of analog behavior that are synthesizable on an FPGA called MSDSL to implement some of the analog behavior that we added to our instrumentation. Last but not least, we wanted to assure ease of use by, on the one hand, incorporating a very well way of working. So effectively, this means using our methodology or framework is very similar to how you would work post-silicon in a lab. And also we employed a significant amount of abstraction and automation to make sure that the validation engineer doesn't have to worry about FPGA specific aspects. So let's have a look at one of the two main modules we built, which is the analog event capture unit. On the left and right, you can see the mux structures, which I mentioned before. The inputs can be connected to any specified signal of the device under test, and the output can be connected to any other instrumentation block of the top level. For example, the time manager or the trace unit. The cores themselves are mainly runtime reconfigurable. So you could, for example, change sensitivity and polarity and also repurpose the core entirely to be, rather than tracking a limit crossing, observing a period. We added a configuration layer to pre-configure these cores individually. Here you can see how trigger 1 as 1A analog event capture unit core can be configured. You can make use of the NSMod scripting API to conduct entire experiments, also to reconfigure any of those cores. In this example, the AEC core called trigger 1 is repurposed to be a pulse width trigger, and also the interval within which it is checking was reconfigured. This is how the entire top level of the FPGA looks like. On the bottom, you can see the device under test, and on the left and right above that, the analog event capture unit we built, and also this stimulus generator unit. The remainder of the instrumentation was reused from NSMod, including a time manager to pause the emulation, trace unit to record signals, and control IO unit to reconfigure any signal of the instrumentation or device under test during runtime. Let's have a look on how it is possible with this infrastructure to record a signal. First of all, you need to send a 0 time step request to the time manager to pause the emulation. After that, you can configure using the control IO unit the analog event capture unit's input signal, which it should trace. The connectivity needs to be set to the trace unit, and also the capture condition can be set accordingly. Further, you can configure the trace unit to assure that it will trace as soon as there's an activity on the analog event capture unit's port. And last, you can resume emulation by setting a maximum time step request to the time manager. To show you how this methodology is used in practice, I'm using the application of a microcontroller-based power controller, where on the top you can see the application circuit, and on the bottom the power controller. The way it works is that the power controller measures the output voltage, input voltage, and also the switching currents, here represented as IL1 and 2. Through digital filtering and nonlinear control functions, these signals are processed, and the PWM signal, which drives the switches, is controlled. Switches here are shown as HS12 and LS12. The entire functionality is partitioned across various different analog and digital IPs, including firmware. So the two scenarios I would like to focus on is, on the one hand, protection. Whenever a safety feature usually occurs, this results in a false shutdown during normal operation. And the example I'm showing here, there was a current spike in the ADC sampling, which caused an interrupt to occur and the PWM signal to shut down. Using our methodology, it is possible to pause the emulation at the point in time where the interrupt occurs, and then using the stimulus generator unit, you can stimulate signals to quickly analyze possible root causes for the shutdown. The second experiment is regulation. During regulation, one of the most important aspects to look for is the ripple on the output voltage, which is initially analyzed using classic regulation theory. However, since the system is not linear, the actual response of the system will differ from theory. And in order to analyze the response, you need to be able to observe state variables of the application circuit and the regulation code simultaneously at different points of the AC input line. Using our methodology, the AC and ST unit, you can observe or analyze these variables and also replay them for different configurations to better understand the deviation between the actual system response and the theoretical one. In order to conduct those experiments, we made use of two analog event capture cores, one to observe the PWM signal and another one to observe any voltage or current in parallel, and three stimulus generator cores to represent the AC source, the output load, and also inject stimuli. From a resource perspective, we had an increase in auxiliary instrumentation. This accounts, for example, for additional connections to other instrumentation. We needed to spend more resources for the stimulus generator cores and also the analog event capture unit cores. Here I split the resources into capture type specific ones, which account, for example, for the functionality to trace a certain voltage level, and shared resources that account for routing and also common options like a timeout or a delay. From a timing perspective, we used a VC707 board, including a Vertex 7, to run bitstream generation twice, once with and the second run without instrumentation. In both cases, we were able to run with 50 megahertz. However, the worst negative slack did degrade, which resulted in a theoretical simulation throughput reduction of 2.7%. What I've showed you is a framework that allows effective and systematic analysis of AMS applications that are run on FPGA on the example of a microcontroller-based power controller. The main advantages of the framework are simulator-like analysis debug capabilities. As everything is virtual, there's no risk of damage, and analysis can be conducted nearly in real time. Seamless integration of the instrumentation library into NSMod assures a low overhead when employing this framework. That concludes my talk. Thanks a lot for your attention, and I would be happy for questions to answer questions.
Thank you very much. Any question by the attendees? I have, so I'm going to start. Is it an intrusive tool? I mean, when you do your measure or instrumentation, do you modify even a little bit the behavior of the system under test?
Right now, theoretically, yes, because we don't use partial synthesis. However, this is an optimization for the future that we're targeting.
Okay. Any other question?
Yes, I can just have a small question regarding the application of this approach, AMS application. So you have presented an application to MCU based power controller. Is there any limitations in terms of the applicability of this approach for these AMS circuits, or?
So the event capture unit has a specific set of capabilities and features. And if you, for example, are interested in a specific aspect that is currently not covered, then you wouldn't be able to see it, at least not with this instrumentation. So far, we try to implement most of the features that are available for oscilloscopes. So the likelihood of this to be happening is rather limited. The bigger limitation usually occurs when the application circuit grows too big.
Any constraints with respect to the FPGA technologies, or I mean, it's you have used the Vertex 7 to to implement this, is there any specific requirements with the target FPGA circuit, or?
I mean, in general, when you host mixed signal emulations on an FPGA, you rather quickly need a significant amount of these P slices. And usually the limitation comes from the application circuit of interest, not too specifically the instrumentation that we built.
Okay.
Yeah, and also
Okay.
record. Yeah.
Okay. Thank you again for the presentation, and we will switch to the next speaker. So it seems to me I have seen Ritwik Sina, probably.
Yeah, hi. Am I audible? If yes, then I'll start sharing my screen.
Yeah.
Okay. I hope it is visible enough.
Yep.
Okay, so
maybe you can put it in the full screen. Yep.
Yeah. 1 minute. It's lagging a little bit.
It's a black.
Yeah. It's lagging a little. Just excuse me for 1 minute. Oh yeah. Is it visible now?
Yep. Perfect.
Yeah. Okay. So the topic for the talk is machine learning based hard-soft logic trade-offs in VDR. So where does the relevance lie is of the project is in the scientific community who works on digital circuit analysis, and end users such as, for example, a robot manufacturer who wants to make a custom and cheaper robots. So if the project is utilized at its full potential, it will give the end user efficient robots which consume less power, have longer battery life, suitable for real-time tasks. So it's all very custom, and the end user will provide their requirements, and according to those requirements, it can be modified enough to give them the best suitable result. So the project tackles few of the deficiencies of previous work, which includes that the existing tools that are there, though they are very efficient, but they need to be updated with the ongoing update in software technology. The information taken from the hard-soft logic trade-off has to be used more intelligently, wherein the proper placement or the proper proportion of hard and soft logic blocks should be made so that they give us a better result. And there is a need to reduce the time spent manually in determining this mix of hard and soft logic block, and thus there is a need for automation of it. The proposed approach here is to find a proper ratio of hard and soft logic blocks, and then training a machine learning algorithm that will predict optimal ratios for the incoming new circuits. And as I said, depending upon your application, your custom requirements, the ratio may change, and thus it will give us a very tailored result for the application. The data collection was done by running the VDR flow for different benchmarks with different ratio of hard and soft logic blocks, and then an optimal ratio was taken out, and then the machine was trained on it. 11 different classifiers were trained on it, and the results were analyzed. So the VDR pipe, the Verilog to routing flow was used for it, and the VDR pipeline includes 3 basic tools: Odin2, ABC, and the VPR. So Odin2 acts as the front-end tool, which, as you see, takes in the input of the architecture and HDL file, parses and elaborates it, and gives us a raw netlist. This netlist has the information regarding the input parameters, which is given to a trained machine learning model here in green. And this machine learning model uses that input to predict an optimal multiplier ratio, which is then fed as further information to the partial technology mapping phase, which is utilized enough to make a technology map netlist, that is a netlist that is aware of the architecture criteria. And then logic elimination occurs, in which we remove unused logic, and then it's stored in a blip file and later forwarded to ABC and VPR to do further modifications on it. So why machine learning? Machine learning is an approach that relies on feature vectors, or how to explain a feature vector is that it will compromise of different elements that will be connected to one object. Like if there are 4 features as in the example, then these 4 features would be connected to one object, and changing or like with different features, a different object can be determined. So the feature vectors that were included in the data set were the memory hard blocks, the number of digital circuit signal processor blocks, pre-packed netlist, and the critical path delay, out of which the critical path delay acts as a very critical feature vector here, because in the project we targeted having a circuit that has the least critical path delay, so that it gives us a very fast circuit. So where is this model placed in the VDR pipeline is, as you can see, Odin 2 is represented in yellow, then ABC in almost aqua color, and then blue for VPR. At the end of VPR, we get a very fine-tuned data that is having all the timing and placing and routing information stored with it. Then we make a data set from that. We do for some pre-processing, and if you follow the green flow here, and then we train our machine learning classifier and we save it. Now this saved machine learning model is placed in between Odin 2 before partial technology mapping, so that if incoming new data is encountered, then this machine is trained enough to predict an optimal ratio, so that for the new data, we can have modifications at an earlier stage, and this intelligence can be utilized to give better routing and timing results. Since this was a classification task of classifying which is an optimal ratio, we used 4 metrics: confusion matrix, accuracy, precision, and recall for our evaluation. So as I said, we used a few benchmarks in which we divided the ratios of hard and soft logic block into different categories from 0% to 100% with a step of 5%. Then all these classes were label encoded during the pre-processing stage. And then using this data set, new created data set, 11 machine learning classifiers were trained and evaluated, and a comparative analysis was done on them. So if you can see here, we used these 5 benchmarks from different domains, and we used architecture, like used excuse me for this. We used architecture files of different features for it. And then 3 data sets were created, out of which dataset D1 was created when Odin 2 was used as a front-end tool. Then D2 was created when we used Yosis as an elaborator to come up with better support for language. And then Odin 2 was used for partial mapping here. Later on, a combined data set of these two was made and was given the name D3, and the training was done on D1 and D3, and then a comparison was done. So after the comparison and analysis, we see that out of all these classifiers, decision tree happens to perform the very best and scoring an accuracy of 86% on a combined data set and 78.57 on a single data set. Thus, we see how different classifiers can have different outcomes. And if we choose an optimal classifier for our tailor-made application, we can have better suited circuits for our application, and thus we'll face no delays or lags or any kind of roadblocks for our application. And if you can see the previous graph, in which we see gradient boosting is having almost an equal accuracy as of decision tree, but using these 4 metrics, we can determine that accuracy, precision, and recall were greater for a decision tree than for gradient boosting. So if we change our application, maybe a gradient boosting performs better than decision tree, and then we need to change our training. So it is very custom and tailor-made for the application, wherein you can have your best classifier and which can predict better ratios for you. For the benchmarks used, the data set was non-linear and it was a well-structured data, and thus it made decision tree to perform best, having a training accuracy of 85.91% and a test accuracy of 86, emphasizing that it does not overfit and it's actually performing good, which can be seen in this confusion matrix. As you can see that on the primary diagonal, we have 22 data points, of which the ratio class was 6 and it was predicted as 6. And then 10 cases where it was 1 and it was predicted as 1. Few cases where, for example, it was 0 and it was predicted as 1. So if you can see the primary diagonal, there are 43 data points, and out of all 50 data points here in this example, so it performs with an accuracy of 86%, giving an improvement to the VTR flow, making the partial mapper much more intelligent here, and giving us a fast circuit as was predetermined in the application of the project. Contributions of the project include a literature survey done for various circuit optimization techniques, improvement to the VTR flow, making the partial mapper intelligent, and a combination of data sets that was created, which can be further utilized to enhance the data set or to make new data set to have much better results. Maybe, yes, which comes as a future work in which we see that all this research was done taking into account the multiplier ratio. Similar approach can be applied to adder ratio, and maybe these two classifiers can be combined to have an average requirement satisfied. Then an intensive comparative analysis of more classifiers can be done here, uh, so as to get maybe to get a better result than this, maybe not. And yeah, that's it from my side. Thank you.
Thank you very much. Any question in the audience?
And
No?
I'm up for any questions if you have.
Yeah, so I can start. So what you have provided or what you have presented in this work is more or less an estimation performance tool. Would it be possible to have developed it outside of Odin 2? Or because it seems to me that you use Odin 2 just for the parsing, more or less. So I mean, yeah, is it possible to make something similar outside of Odin 2, but I don't know, with an industrial tool, or just, okay, I can understand that parsing the code is necessary. But after that, is it possible to use another tool?
Yes, you raise a very interesting point here. So the VTR pipeline was used to collect data set, to make a data set here and train classifiers. Once this classifier is saved, it can be used anywhere, wherein we parse an HDL file and get these information, and later technology mapping can be done on that.
And similar question is this kind of, I would say, performance estimation for all that probably more or less depends on the tool, because depending on the synthesis tool, you may have more or less adder, multiplier, I don't know, different hardware resources. So does it mean that for each tool, you probably need to have machine learning approach, a specific machine learning approach, and then a different result depending on the tool?
So now maybe yes, we need to analyze what kind of information are we getting from the tool and how we can utilize that information. And depending upon that, yes, we can train different classifiers and have results on basis of whatever tool we want to use here.
Okay. Any other question?
Yes, I have a question.
Amer, please.
Can you go, please, back to slide 13?
Yes.
Yes. Just again, I missed how you compute this accuracy Yeah, how the accuracy has been computed for these different data sets.
Okay, so two data sets were there, D1 and D3 as described here. And using these two data sets, these 11 classifiers were trained with the help of scikit-learn library. And as a result of which we can compute accuracies like I showed here, that when the ratio classes were divided. So there are 6 label encoded classes here. And when it is actually 0, in one of the cases, it predicts 0. When it is actually 1, in 10 cases, it predicts 1. So this way, on a primary diagonal, we can see having 43 data points against 50, giving an accuracy of 86%. So this result was for decision tree, and thus this map can be plotted for, I mean, almost all 11 classifiers as well.
Okay. And in the
Okay.
future work, you are saying that one of the future work will be to explore other classifiers.
Yes. So one of the future works is intensive comparative analysis with more classifiers. So as we see that these are not the only 11 machine learning classifiers available, but maybe more classifiers can be trained on this. Maybe the dataset can be enhanced. More benchmarks can be used, and then on the basis of which we can have a better comparative analysis in future.
And regarding applying this approach to the other ratio with respect to multiplier, it will be the same approach. What you expect as
Yeah, so I expect a similar approach here. Since we had a platform for tweaking the multiplier ratio, this project was done with the multiplier ratio. Once a platform for tweaking adder ratio is available, developed properly, then we can do the similar approach for adder ratio as well. And for different ratios, we can have different requirements. For example, we want to have a circuit which is compact. Okay, so given different adder ratios, we can see which circuit consumes less area, and then that ratio would be an optimal ratio for the application. And giving this information to the machine, we can train it, and it will then predict for future circuits.
Okay, thank you.
Okay, thank you again for this talk. I will just put a last slide to conclude this workshop.
Yes.
Yep. So I don't know, Ken, you hand this workshop. Okay. So Ken, I don't know, do you have a word for the end of the session of this workshop?
Hopefully it will be face to face the next time.
Definitely face to face next time. It's way too long since we've gotten to see people face to face and have some of those interesting chats.
Yeah, it has been. This is the third edition virtual, right?
Third or second? I don't know.
20, 21, and 22. Yeah.
Yeah. Okay.
Yeah, it's third time.
Okay.
Third time. Hopefully, yeah.
So yeah, so I would like to thank all the attendees, the TPC, the program chairs, and of course my friends Kenneth Ken as a general chair, and all the people at ESWeek who have worked for RSP or to be able to make it running this year again, even if it's in virtual. But okay. It has a lot of work and a lot of exchanges, emails, and so on. So thank you very much, and I would say good night for people who are in Europe and in Asia, and good day for people in North America or South America. Okay, bye bye.
Yeah, thank you.
Hope to see you next time. Bye bye.
Bye all. Are you stay there for a second, Amir?
Yeah.
Yep.
Yeah, you too, Fred, if you want.
Yeah. Hi, Ashok. Bye bye.
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 Bye-bye. Thank you.
Yes. Hello, guys.
Yeah, we should probably stop the recording, or
Yeah.
I don't know if someone from the ESWeek
not master or...
is okay to stop the recording. Not
stuff,
sure.
yes, ESWeek stuff is.
I don't think I'm able to stop it.
No.
Okay. Let me.
Otherwise, I can. Do you wish that I create a link and send you?
Yeah, it's what I wanted to do, but it's a Zoom, so okay. Yeah, I suggest to do that. I open a Zoom.
Yeah,
room
can you
and,
send? Can you send us a room?
no, but I cannot because Zoom is running, so I can open another.
No, we have to quit.
By email, and I send you by email.
Yeah,
okay?
by email, send us.
Okay.
Yeah.
Sure. All right. I'll
Yes,
see you there
bye.
when you send an
Yeah,
email.
bye.
Bye.